Saturation is one of the most important concepts in music production, but most of the explanations about what it is and why we use it are pretty vague. Saturation, along with EQ and compression, are the most important tools we have at our disposal. Now, before we learn how to properly use saturation, it's good to know how it works. Now, this video is going to get pretty deep, but I promise if you make it through, you'll learn something new about some fundamental ideas in audio. I gotta warn you though, if you're looking for quick saturation tips, this isn't your video. Now, before we go any further, I have to clarify. Some people call it distortion, some people call it overdrive, drive, fuzz, warmth, grit. Some plebs even call it gain. But in this video, I'm gonna call it what I think is the most umbrella term that music producers use, which is saturation. What is saturation? Saturation changes the shape of a wave, and it does this in such a way that it adds new frequencies to that wave. An EQ changes what's already there, but a saturator adds stuff that wasn't there before. Saturation is important for two reasons. It compresses sounds, so it lowers dynamic range and can help glue a sound or group of sounds together. It also adds new frequencies, which can make a mix sound more full or more tonally interesting. Saturation is what's called a nonlinear process, which is just a fancy way of saying changing the input by a certain amount changes the output by a disproportional amount. Put simply, saturation takes the amplitude at each point in the wave and scales it to another value, changing the shape of the wave. In fact, another word for saturation is wave shaping. Let's take it slow. Let's just look at half a sine wave for now. The way wave shaping is usually visualized is like this. The x-axis of this graph represents the input level of the wave. So low amplitudes are down here and high amplitudes are up here. The y-axis of this graph represents the output amplitudes of the wave. Again, low amplitudes are down here, high amplitudes up here. The thing that connects the input to the output is our saturation curve. Right now, the saturation curve is a line. So this point on the wave will be scaled to the same output, so the wave remains unchanged. It's linear. However, if I add a slight curve to this, it becomes a non-linearity. The input amplitudes don't equal the same output amplitudes. For example, this point on the wave will be scaled to this amplitude now. Now, by doing this, I've changed the shape of the wave, and this means that I've changed the frequencies that make it up. Saturation is taking every point on the wave and scaling it by some amount. We take a point on the wave, stick it on the x-axis, and find how the curve changes that point. Okay, so far we've only been dealing with the positive parts of the wave. What the fuck is that? You try to make a professional YouTube video. Anyway, where were we? So far we've been dealing with the positive parts of the wave. You might have noticed though that waves tend to be wavy. Waves aren't just made up of hills, there's also valleys, just like life. Now this entire time, the x-axis has only represented positive amplitudes, from 0 up to the maximum, but we're missing all the negative amplitudes a wave can have. So we have to extend our graph to include negative amplitudes. Now it's getting tricky. We can affect the wave differently when it's above the x-axis than when it's below the x-axis. Remember, when we're looking at the wave itself, we're looking at amplitude over time. When we're looking at a saturator, we're looking at the input amplitude versus the output amplitude. So everything I talked about earlier can be applied to the bottom part of the wave. And changing the top of the wave differently from the bottom has some interesting effects, which I'll talk about later. That fucking light. Pop quiz time. I hope you've been taking notes. If I have a sine wave and I pass it into this curve, what would it look like after? This last one is just the original wave with its phase flipped. If you got those correct, congrats. So this is fun, but how does any of this pertain to what we hear? When we change the shape of the wave, new frequencies are added to the sound. More precisely, harmonics are created. Harmonics are whole number multiples of the fundamental frequency. So for a wave with a fundamental at 100 Hz, the second harmonic would be 200 Hz, the third harmonic 300 Hz, and so on. But this begs a question. Why does changing the shape of the wave add frequencies? Think of what changing the shape of the wave actually means. Let's use our old friend the sine wave. Sine waves are pure tones, meaning they're made up of one frequency. Let's assume there's no phase shift, so the shape of the wave only changes due to saturation. If I clip the peak, I'm changing the shape of the wave. But one way to look at it is that instead of me clipping the wave, I'm adding on a new wave that looks like this. This is because this new wave is doing the same thing as the sine, just flipped upside down. So when we take our sine wave and add this new wave, the peaks of the sine are canceled, giving us the clipped wave. These two ideas are equivalent, so changing the shape of the wave in any way must change the frequency content. The added frequencies from clipping are just the frequencies of this new wave. Okay, so saturation changes the shape of a wave, which adds new frequencies. But what's the relationship between the saturation curve and the harmonics added to our wave? There are two kinds of saturation curves, symmetric and asymmetric. A symmetric curve means what's on the left side is symmetric with what's on the right side, whereas an asymmetric curve is one where the left side isn't symmetric with the right side. Now, we're going to go into depth about both these cases, and hopefully by the end of this, you'll understand that everything that has to do with saturation and distortion and all this stuff comes down to this interplay between symmetry and asymmetry. Let's start with symmetric. Like I said, symmetric curves have a symmetry between the left and right side. For example, this is a symmetric curve. More precisely, it's called an odd symmetric curve because the left side is the opposite of the right side. It's odd because most saturation curves that look like this can be represented as equations with odd powers of x. For example, x to the power of 3 gives this curve. The left side is the opposite of the right side. This makes sense because say x equals 1, then the output is 1 to the power of 3, which is 1. But if the input is -1, -1 to the power of 3 is -1. I promise we're almost done with the math. This odd symmetry where the left side is the opposite of the right side adds odd harmonics to our sine wave. In this case, it would add the third harmonic. The same thing also applies to any combination of odd curves. Now, the classic saturation curve most people are used to looks something like this. So if we send a sine wave through it, the added harmonics will all be odd, and there will be infinitely many of them. Remember what harmonics are. They're whole number multiples of the fundamental frequency. So the odd harmonics would be 1, which is the fundamental, 3, 5, 7, 9, and so on. What it comes down to is this. When the left side of the saturation curve is the opposite of the right side, you affect the top and bottom parts of the wave in the same way, and this creates odd harmonics. And as you can see, it pushes our sine wave to be more square-like. In fact, a square wave is made up completely of all the odd harmonics. But all this math aside, why does affecting the bottom and top part of a sine create odd harmonics? And why do odd harmonics create square waves? Sine waves exhibit a property called half-wave symmetry. This means if we draw a line down the center, the two sides are opposites. Now we know odd saturation curves saturate the top and bottom parts of the wave in the same way. This forces odd harmonics to be created. The easiest way to understand why is to look at another symmetry sine waves have. If we just look at half the wave, there's another symmetry down the middle. This is called quarter wave symmetry. As we start to saturate the sine and get closer to a square wave, we can see the symmetry is still there. Odd saturation curves preserve these symmetries, and because of this, only odd harmonics can be created. Let's look at the first 3 harmonics of a square wave. So the first harmonic, the third harmonic, and the fifth harmonic. This is what the wave looks like, and you can see it kind of has that square shape. Now let's just look at half the wave right now. This wave has quarter wave symmetry. The 3 harmonics that make up this wave look like this. If we look at the fundamental, for every hump of the fundamental, odd harmonics have an odd number of humps. For example, the third harmonic has 3 humps, while the fifth harmonic has 5. This means that there's no way you can have an equal number of humps above and below the 0 point. Like if you have an odd number of things and you try to divvy them up evenly, there's going to be one left over that you have to put on one of the sides. Because of this, there's a symmetry down the middle, and so the composite wave must be the same on either side. Now if we look at the other half of the wave, it's the exact same. All the harmonics are just flipped upside down. Shaping the top and bottom in the same way forces the only possible harmonics to be odd harmonics, because those are the harmonics that give humps in the right places to preserve this symmetry. Any wave that has half wave or quarter wave symmetry is made completely up of odd harmonics, and this is why square waves are purely odd harmonics. Triangle waves also have this symmetry and are also completely made up of odd harmonics, although it gets a little weirder. Just like before, For there to be a symmetry over half a cycle of the wave, for every hump of the fundamental, each harmonic must have an odd number of humps. However, unlike square waves, every other harmonic has its phase flipped 180 degrees, so it alternates back and forth. This causes all the humps to overlap in the center, but the humps cancel out more and more the closer you get to the edge. And the more harmonics you have, the steadier the wave moves towards the 0 point. In the square wave's case, when you're near the edge, the harmonics stack on top of each other. So the more harmonics you have, the less steady the wave will move towards the 0 point. If you have a perfect square wave with an infinite number of harmonics, it doesn't approach the 0 point at all. Not even here. It just jumps instantaneously to the bottom. There's another difference between square and triangle waves. The harmonics of triangle waves fall off faster than square waves. With square waves, the amplitudes of the harmonics decrease with the harmonic number. So if my fundamental has an amplitude of 1, the third harmonic is a third as high, the fifth is a fifth, and so on. But with triangle waves, the amplitude of the harmonics decreases with the square of the harmonic number. So if my fundamental is at 1, the third harmonic is only 1/9 as high. The fifth is 1/25. This causes triangle waves to sound less harsh to our ears because the higher dissonant harmonics sound quieter. There's also an intuitive reason for why this is, but it's a little convoluted. I might make a video about it, but I want to stay on topic. There's a lot to cover. Odd harmonics tend to sound harsher to our ears, and this is because they're at more dissonant musical intervals. And I'm going to show you what I mean by that. I'm going to play all the odd harmonics and take this low-pass filter and just slowly sweep it up the spectrum to bring each odd harmonic in so that you can hear the dissonance. So the higher you go, the more dissonant the tones become. So we know what happens when a curve has odd symmetry. What about when it has even symmetry? When the left side is the mirror image of the right side. If we pass a sine wave into this, only even harmonics would be created. Similar to before, curves that have even symmetry can be represented as even powers of x. This means sending a sound into a saturator with an even curve like this spits out a wave where the bottom part becomes the same as the top part. Not equal and opposite like odd curves, but the exact same. Now in practice, this usually means the positive part is remaining the same and the bottom part is being flipped to be positive also. This is called rectification. And for a sine wave, it adds even harmonics. So what we're left with are the second harmonic, the fourth harmonic, sixth, eighth, and so on. You'll notice though that the fundamental is gone because the fundamental is the first harmonic and 1 is an odd number. Wait, what? What happened to the fundamental? All we did was flip the bottom part of the wave to the top. All of the wave is still there. So where did that frequency go? Well, to answer that, we need to know what is a fundamental frequency. A fundamental frequency is determined by the time it takes a wave to repeat itself, called an oscillation. If I have a wave that did 1 full oscillation in 1 second, it would be a 1 Hertz wave. But when I flip the negative part of the wave to be positive, all of a sudden, what was originally 1 oscillation turns into 2 oscillations because the wave now repeats itself over a shorter time. So the length of 1 oscillation is now half a second or 2 Hertz. By flipping the negative parts of the wave to be positive, we've doubled the fundamental frequency. So is that frequency lost forever? Is there a way for us to have even harmonics with the fundamental still? There is. If we just take the left side of the curve and put it to 0. This adds the fundamental back and keeps all of the even harmonics. What was originally 2 oscillations now goes back to being 1 oscillation. The basic shape that's made up of even harmonics doesn't change. It just repeats itself half as frequently. This is called half-wave rectification. Even harmonics don't sound as harsh as odd harmonics, and this is because they're at more stable musical intervals. And you can hear it if I just play the even harmonics. Even harmonics just sound more buttery. Okay, so odd curves give odd harmonics to our sine. Even curves give even harmonics. Crazy. Small caveat to this. Rectifying a square wave flips the bottom part of the wave and gives silence. A nice warm DC offset. But DC offset is a frequency of 0, and so you can think about it as the 0th harmonic. So this rule, I guess, still holds. What if I don't make our curve symmetric at all? So the left side is different than the right side. If I send a sine wave through it now, both even and odd harmonics are created. The closer the curve is to an odd curve, the more odd harmonics are created. And the closer it is to an even curve, the more even harmonics are created. Now, I gotta remind you that I've been using sine waves this entire time. However, you might have realized in your time listening to music that most people don't play sine waves. Real instruments and synthesized sounds have much more complex frequency distributions, and you can't necessarily know what the new frequencies will be just by looking at the saturation curve. Harmonic distortion technically only means distorting a sine wave. If there's any other frequencies present, you'll get harmonic distortion's big brother, intermodulation distortion, which is much more complicated. So this is a really important point. Probably the most important thing in this video. What you're passing into your distortion plugin is just as important, if not more important, than how you're distorting it. The best sounding distortion comes from properly processing the sound before you even send it into your distortion. And I'm gonna do a whole video on that. So I think this video is a good introduction to the basics of saturation and harmonics, but the next few videos I'm gonna be talking about specific saturation techniques and a bunch of the different kinds of saturation and how we can use the principles in this video to get the sound we want. As of right now, that video is not made. So I want to hear from you guys. What are you guys curious about with saturation? Are you struggling with anything in particular? And not just in music, maybe just in life. Let me know below. Thanks for watching.